one more application of interference that deals with this extra distance. It's called thin film interference.
Isn't this what rain does?
I'm sorry, what?
Isn't this what rain does? With like the grease and such?
Yes. So if you've ever been in a parking lot after it's rained and it's now sunny, a lot of times you'll see little rainbows in the puddles, and that's because there's a thin layer of oil on top of the water. That thin layer of oil is a thin film, and therefore we get thin film interference. So number one, you have to have something thin, very, very thin. A layer of something. So we have three layers here. So for example, this oil on water. We have air, then we have a thin film of oil, then we have a puddle of water. And then we, of course, have the parking lot, the asphalt, but that's not important in this particular
So
matter.
is that why, so like with the clouds, when we get a rainbow in the clouds, is it just like thin compared to the distance from the sun?
No, the rainbow from the clouds is due to refraction within, and total internal reflection within the water droplets. So it's a little bit different of a application. Index of refraction. Remember, light travels at different speeds depending upon the material, and it's the index of refraction that determines how fast light travels. So as light comes into oil, it's going to slow down. As it goes into water, it will slow down even more. Turns out, since the speed changes, so the speed of the light in another medium is equal to the speed of light in the vacuum, which is pretty much the same as speed of light in air. Technically, N for air is like 1.000 something. It's close enough to 1. We tend to use 1 for air. Turns out, as light enters a new medium, the frequency stays the same. So the frequency at which the electric field is oscillating at does not change as it goes from, say, air to oil to water. But if the speed changes and the frequency stays the same, then the wavelength must change as well. So the wavelength of the light changes as it goes into a new medium. The relationship is just like the speed relationship. Because remember, speed is equal to frequency times wavelength. If speed is decreased by a factor of n, then the wavelength is also decreased by a factor of n. Okay. Yes?
So when it's going from oil to water, the wavelength of n is equal to the wavelength of oil divided by water.
No, the wavelength in the water would still be whatever the wavelength in the air was over the 1.33.
Okay.
If you want to relate the wavelength in the oil to the wavelength in the water, you can set, since the wavelength in the air would be n times the wavelength in that material, you can set n times the wavelength equal to n times the wavelength. Okay? Question?
Yeah, as light then goes through the atmosphere, is it going from 0, n equals 0 to n equals 1?
No, n equals 1 in vacuum.
Oh, as well.
And it's pretty much close enough to be 1 in air as well. So we still say the speed of light is 3 times 10 to the 8th meters per second.
Divided by 0.
I know.
But yeah, the smallest n can be is 1. You cannot have an index of refraction less than 1. So even a vacuum is 1.
Actually, some of the nano cloak things,
Oh, yeah?
those change the index of refraction using nanoparticles to make it slightly less than 1.
Cool.
Oh, nice.
Learn something new every day. That's awesome. Okay. Now us. So we're up here looking down in this puddle. The whole reason we're seeing interference is because of reflection. As light is coming in, some of the light will reflect off of this first boundary between the air and the oil. Some of it will transmit through. Okay? So some reflects, some of it goes straight through, some of it will reflect off that next boundary, some of it will go straight through. It's these two reflections that are determining what we see. Okay? Now, we're going to have to come back to this whole delta phi naught business. I said delta phi naught was 0 if the source was emitting identical waves, and delta phi naught was pi if the source was emitting exactly out of phase waves. The original emitter is the sun, so these waves were pretty much in phase as they came in. Delta phi naught is now determined by the reflection. If the two reflected light rays, as they're reflected, if they're in phase or not. Delta phi naught is 0 if the reflected light rays are in phase. It'll be pi if out of phase. Now keep in mind, when a wave reflects off a boundary, if the boundary is rigid, the wave inverts upon reflection. It has a phase shift. If a wave reflects off a loose boundary, it does not invert. So the concept of a rigid boundary versus a loose boundary here with our reflected light rays, basically, if the light is in a lower index of refraction and reflecting off a higher index of refraction, that constitutes a rigid boundary. So this top light ray had a phase change. It was shifted by pi. So it's now exactly opposite of what it was when it came in. This reflected light ray is in oil. It's reflecting off the water layer. Since oil's index of refraction is 1.25, which is less than 1.33, then this reflected light ray also has a phase change of pi. So anytime a light ray is reflecting off a surface where the second surface has a higher index of refraction than the one it's in, there will be a phase change. Keep in mind also, though, whatever transmits through, whatever's not reflecting, does not have a phase change. Okay? It's only the reflecting ones. So right now, the two waves, both of them were in phase before they reflected. Now, once they both reflected here, they both had a phase change. So they've both been shifted by pi. So, what can you tell me? Are they in phase with each other or out of phase?
Out of phase.
Well, one's traveled farther than the other before.
Just due to reflection. We'll throw the distance into it. That's also important.
So
But just due to reflection itself, are they in phase or out of phase with each other?
they're still in phase.
They're still in phase. Both of them shifted by the same amount, so their peaks are still lining up, their valleys are still lining up. So they're both still in phase. So delta phi naught is 0. Which means the equations that we derived yesterday, or last time, for perfect constructive interference, delta x will be m lambda. For destructive interference, delta x will be m plus 1/2 lambda. So the equations we derived are still perfectly valid. Now, please keep in mind, now it doesn't make sense to have m equals 0 for constructive. Because if m is 0, then that means delta x is 0, which means basically you had no thin film. Okay? Delta x is the extra distance the one wave travels versus the other. This bottom wave is traveling farther because it's coming down through this oil layer and back up. Delta x, we'll call that d. If d is the thickness of the layer, then delta x is equal to 2d, because the light had to go down through the layer and back up. If m is 0 in the constructive equation, that means delta x is 0, so you just don't have a thin film. Okay? So really m needs to start at 1 for this equation. M can still start at 0 for this equation. If you don't like them starting at with different M values, if you want the same M values to apply, so M equals 1, 2, 3, so forth, you can change the sign in here to a minus sign, and then M has to start at 1, because it wouldn't make sense to get delta X being a negative anything. So either way is fine.
Wait, is minus a half not plus?
Only if you want M to start at 1. If you want M to start at 0, then it'll be plus. So either equation is fine, you just have to remember which its smallest M value is possible. Okay, so let's go ahead and put 2D in for delta X. Now we're still not quite done. That extra distance the wave is traveling is in the oil layer. This wavelength is going to be, in the oil, it's going to be smaller or shorter than it was out in the air. This needs to be the wavelength of the light in the film itself, whatever your thin layer is. So we can go ahead and put this substitution in, the wavelength over n. And just remember that n is for the film specifically. It's that thin layer. So for example, when you look at the puddle, whatever color you are seeing, that you do see, that's the constructive interference. If you don't see a color, then it's destructively interfering. So let's say we're looking at a puddle and we see red. Now red, really, the wavelength for red is a region. There's varying shades of red. Let's say we have a way to know that we're looking at the wavelength of 6 at 50 nanometers. So we know that that is the color we are seeing. What is the thinnest possible thickness? What's the smallest possible thickness of that oil layer for us to see red? Okay. So if we're seeing red, then we have constructive interference. We can solve for D, the distance, or the thickness of the film. D will simply be m lambda over 2 times n of the film. If we want the thinnest layer possible, then we need the smallest m value possible. The smallest m value possible is 1. Our wavelength is 650 nanometers. The film has an index of refraction of 1.25.
You don't have to convert because we'll get nano.
Yeah, we can just express our answer in nanometers. That's exactly right. So the thinnest possible layer that would allow us to see red would be 260 nanometers. Now that's certainly not the only thickness that would allow us to see red. We can put m equals 2 in here, we get 520 nanometers. 520 nanometer thickness would also allow us to see red. If we put m equals 3 in, that would allow us to see red as well. Okay. The layers, though, have to be very, very thin. We're talking nanometer scale. Because as waves travel through your medium, the amplitude decreases, the intensity decreases. So if this layer gets too thick, the reflected light ray won't be intense enough for us to see interference. So the film needs to be really thin.
So I see, it's pretty much just part of it's getting slowed down and thrown out of phase. And that's pretty much all that's happening.
Yeah. So being thrown out of phase is due to the reflection. In this case, it threw both of them out of phase, so it put them back in phase. And then the extra distance ultimately determines how they meet up. I have another example. This one is two pieces of glass. They're just sitting on each other. You can play with these little screws to tighten and loosen them. If you look down, so keep the pegs up, and you look and get the light reflecting off of it, you can see different colors of rings. Now they're not perfectly circular because of how these different tensions are, but you can see the different rings. So what's the thin film in this case?
Air.
Air. There's a little bit of air between those two pieces of glass. So let's look at that example. I'm just going to modify our picture is all. Now the glass itself is thick enough that it cannot play a role as a thin film. So the only layers I'm going to draw are the two glass pieces and then the air between them. Now I know there's air outside of either glass piece, but the only layer that's thin enough to be considered the thin film is the air in between the two pieces of glass. So we need to first decide which we have. Delta phi naught is 0 or delta phi naught is pi. The top surface, with light being in the glass, reflecting off of air. Glass is 1.5, air is 1. So the reflected light ray here, reflecting off this glass-air interface, since glass has a higher index of refraction than the air, that's like a loose boundary. So there's going to be no phase shift at all. No phase shift for that guy. When any wave reflects off of a loose boundary, it inverts in phase with what it was. It doesn't invert, sorry. It reflects in phase with what it was. So there's no inversion. The second reflected light ray, the light is now in air and it's reflecting off the glass boundary. It's in index of refraction of 1. It's reflecting off index of refraction of 1.5. What's going to happen to that reflected light ray? It's a solid boundary. It's a rigid boundary. So it will have a phase change, or a phase shift, whichever way you want to look at it. So due to reflection alone, one of them has had no phase shift, one of them has had a phase shift of pi. So they were in phase. We had our two waves. Now one of them has had a phase shift of pi, and the other one has not. That puts them out of phase with each other. Delta phi naught is pi in this case. Okay. Which, if we go back to our original equation for delta phi being the k delta x minus delta phi naught, it's the same thing. We can think of this conceptually as well. If they are now pi radians out of phase, that's equivalent to how much of a wavelength? Half. Constructive interference means they are reaching the observer in phase. How do I get these two back into phase? This extra distance, delta x, has to be how many wavelengths to get it back into phase?
Half a wavelength.
Half a wavelength. If they are out of phase by half a wavelength, I need to shift them by another half a wavelength to get them back in phase with each other. The only way to get them back in phase with each other is through the extra distance. So delta x needs to be some multiple of half a wavelength to get them back into phase.
So wouldn't it be just the wavelength over 2 then?
Well, there's multiple, it doesn't have to be exactly 1/2. It could be 1.5, it could be 2.5, it can be 3.5, and so forth. So that's why we're putting the multiple in there. For destructive interference, well, they're already out of phase. We just want to keep them that way. If we want to keep them that way, that extra distance needs to be a multiple of a whole wavelength. And again, these needs to be the wavelength in the film specifically. And I've written it such that M can be 1, 2, 3, so forth. So notice the equations just flip-flopped. If there's phase changes at both surfaces, the last set of equations, this was constructive, this was destructive. If there's a phase change at only one of the surfaces, this flip-flops. This one becomes constructive, this one becomes destructive. Again, we can put 2d in for delta x. We can put lambda over n in for the wavelength in the film. Keep in mind that's the index of refraction of the film specifically. And we could ask similar questions. If we're looking at these little rings and we see red or we see blue, we see a certain wavelength, we can figure out what possible thicknesses it could have. Or we could give us a possible thickness and figure out which wavelengths we could see. Let's look at that. Let's say if the air layer I don't know, 450 nanometers thick. So if our air layer was 450 nanometers thick, or thin, whichever way you want to look at it, what colors could we see? Constructive is what we see. Destructive is we don't see. So our wavelength.
Whereas in the previous example it was constructive we don't see and destructive we see.
No, constructive we see. In either case. So 2D is our 450 nanometers. Our film is the air. Index of refraction of air is simply 1. So what we need to do is plug in a few values of M. For example, if M is 1, we'll get a certain wavelength. If M is 2, we'll get a certain wavelength. So forth. So if M is 1, we get 1/2 in the denominator. The wavelength would be 1800 nanometers. That's not visible. We can't see that. Visible light lies between 400 and 700 nanometers. So this is not something we would be able to see. If we put in M equals 2, we're going to get 1.5. 600 nanometers. So that's a color we would be able to see. That would be a reddish orangish color. If we put in M equals 3, the denominator is 2.5. We're right back out of the visible range. So there's only one color we would be able to see with that specific thickness. So the little rings that I sent around for you to look at, did you see just one color? No, there were multiple colors. Where did it end up? Okay. Do you mind bringing it up so these guys can see it? What can that tell you, since you're seeing different colors? You're seeing more than just red. In some places you see red, in some places you see blue or violet. What would that tell you about the thickness? It varies. Exactly right. The thickness is not uniform. So you're getting constructive interference for different colors. In some places it's red, some places it's blue,
So
and so
when you
forth.
put a box around 600 specifically,
Because that's the only one in the visible range. These are not within the visible range of color. So visible light is between 400 and 700 nanometers.
So it would be ultraviolet and the other one would be infrared.
Exactly.
so even though it probably is refracting at those, it's not.
We just can't see it. Our eyes are not capable of seeing those.
Couldn't it be also super thin, and we see lots of little M's, like
Uh-huh.
M1 through 40 or whatever?
Yeah, if it
That's
was
enough
thin
to
enough,
cause a
there
gradient.
could be multiple M values that work, certainly.